At Balchem Animal Nutrition and Health, we strive every day to deliver results you can see in your animal's productivity and your bottom line. From a smooth transition into the milking string for your fresh cows, to a happy welcome home from your furry friend. From a strong start in your poultry flock, to consistent weight gains for your finishing hogs. We expect to earn your business and your trust with our people, our products, and our science. Our people have an intense passion for your animals and your success. You can count on us for honest, candid advice and practical solutions for your toughest challenges. As the global leader in choline production, chelation, and encapsulation technology, we take our obligation to you and to the environment seriously. Our products are backed by the most extensive and thorough research portfolio, while our business is committed to advancing environmental sustainability and animal welfare. In the end, it all comes down to results. Balchem delivers real results you can count on, results that exceed your expectations, and results that bring true value to your bottom line. Leading the charge to meet the nutritional needs of ruminants, monogastrics, and companion animals, Balchem offers a growing portfolio of nutritional products and a dedication to innovation and industry sustainability. Balchem is here to solve today and shape tomorrow.
Hello everyone, my name is Scott Sorrell, Director of Global Marketing for Balchem Corporation, and I'll be your moderator today. Welcome to the first in our series of webinars for the swine and poultry markets. To kick off this series, we are tackling one of the hottest topics today, African swine fever. Today's Real Science webinar is titled Insights into a Common Goal, Stopping the Spread of African Swine Fever, presented by Dr. Scott D. from Pipestone Veterinary Services. I would now like to introduce Dr. Scott D. Dr. D earned his DVM, MS, and PhD from the University of Minnesota and is a board-certified veterinary microbiologist and past president of the AASV. Scott spent 12 years working in a swine practice before transitioning to professor at the University of Minnesota College of Veterinary Medicine. There, he focused his research on transmission and biosecurity of PRRSV, commonly referred to as PRRS, for the next 12 years. In 2011, Dr. D joined Pipestone Veterinary Services in Pipestone, Minnesota, where he currently serves as director of Pipestone Applied Research, a business unit which conducts collaborative research efforts with production companies across North America, comprising approximately 1.5 million sows. Scott has been awarded $8.8 million in research funds, has published 157 papers in peer-reviewed journals, including the initial publication providing proof of concept of PEDV, transmission in feed, and is currently studying the transboundary risk of pathogen spread through feed ingredients. He has received the AASV Practitioner of the Year Award and the Lehman Science and Practice Award and the AASV Howard Dunn Memorial Award. Dr. D, it's a pleasure having you with us today. The floor is now yours.
Thank you, Scott. Thanks, Balchem. This is going to be a lot of fun. I'm really looking forward to the next hour, and we can go beyond that. If you've got questions and discussion, I'm looking forward to it. I'm going to talk to you about my favorite subject, ASF, and the risk that feed presents as a vehicle for viral movement, not only domestically, but transboundary-wise. So thanks to Balchem, thanks to Scott Sorrell, Stephanie Cocchiara, Kim Jones, and my old friend from Pipestone, Bill Bayless, for kind of connecting me with Balchem. So let's get rolling. First of all, to acknowledge the organizations that have supported all this work, Foundation for Food and Agriculture Research, SAM Nutrition, Swine Health Information Center. Several universities have also helped me move this feed risk issue forward. Eric Nelson from South Dakota State University, Diego Diel, who is at South Dakota State, now at Cornell, Megan Niederwerder and Cassie Jones from Kansas State, you'll hear their names throughout the day, Jeff Zimmerman Iowa State. So it's great working with these fine scientists at how they've reproduced, replicated, and expanded some of the original work we did back in 2014. Minnesota Board of Animal Health has also been very generous, and Dr. Gil Patterson from VetNow has also played a major role. So thanks to everybody. So everybody kick back, get a cup of coffee, relax in your favorite chair. I pulled some volumes off the shelf for the story today. We're going to go through some brief introductions as we'll get into the virus, talk about it, talk about where it is in the world, get into the science of feed as a risk factor for ASF and other foreign animal disease movement, actions and impacts we made so far, and then concluding remarks. Here's my family. That's my wife, Lisa. She's an engineer. There's our daughter, Ellen. She's studying accounting, and our son is at the University of Minnesota in the Public Health Master's Program. You heard a little bit about my background from Scott, so I appreciate that. We'll just go through that real quick. I was a practitioner for 12 years in the field. I went to the University of Minnesota after that to study transmission and biosecurity of viruses, and then with Pipestone. I loved my time at the University of Minnesota, but I wanted to go to a large, aggressive, representative production system, a veterinary system that was moving quickly and looking for ways to enhance their research activities. I wanted to make an impact as fast as I could, and I felt that Pipestone was the place to go. Pipestone's very interesting. The business is called Pipestone Holdings. There's several divisions, so we'll just briefly touch on them. Pipestone Veterinary Services is the group where I'm located. We've got 6 clinics, approximately 40 veterinarians. I think we're one of the largest practices in North America, if not the world. 25 of those veterinarians work strictly with pigs. My research division, Pipestone Applied Research, is present there. We have a division called the Pipestone System, where we actually manage and take care of 75 sow farms, comprising 300,000 sows. We actually will put the group together of family farmers who want to work together. We'll buy the land, we'll build the farm, we'll stock it, we'll run HR, we'll run accounting, we'll run veterinary services, a genetic program. We'll basically run the operation for the farmers, but they own it. That's the 3rd largest system in the US. It's a cool model, and we welcome you to come to visit Pipestone if you have the opportunity. We can also manage the grow finish side if the producers are interested in us helping them from wean to market. There's about over 2 million pigs that are serviced by that division. We can feed the pigs if you want, obviously formulation, procurement, and research in our nutrition division. We can market the animals through contracting, Big Stone Marketing. We can process at Whole Stone Foods. So we can basically do the whole thing if the producers want that, or they can select what service they like us to provide. And then we do have businesses in China and Mexico. We'll talk about a little bit about that. So Pipestone International, which is overseen by my close friend, Dr. Gordon Spronk, the chairman of our board. All right, that's a little bit of background for you, just to give you a little insight into this unique organization called Pipestone. What does it actually consist of? And I'm happy to take questions on it later if you want to discuss. Let's get into the meat of the topic today. Let's talk about 4 viruses of concern. I'm going to go at it from the North American perspective, obviously, but many of you from other countries are worried about these viruses too. Upper left-hand corner, you see foot and mouth disease virus. Below that, you see pseudorabies virus. In the lower left corner, upper right-hand corner, the red tinged electron microscopy is the classical swine fever virus. And then down below is the topic of the day, African swine fever virus. You all understand the rationale for having these conversations and justifying the concern for foreign animal disease entry to our countries, what it does to our animal populations is devastating. As far as the US economy goes, gosh, you can see the estimates in US dollars, in billions of US dollars, that if these 3 viruses entered the country, FMD virus, classical swine fever virus, and African swine fever virus, it's been estimated, in the case of ASF, it's been estimated to 16.5 billion in losses to our economy. Obviously, pork exports would shut down. We export about 30% of our production, which would depress prices. That would depress poultry and beef prices. That would depress grain prices, probably reduce grain exports. Actually, as I read about foreign animal disease entry to other countries, I learned that even tourism goes down. And people don't want to come and visit. They're worried about bringing something back home. And as I read more peer-reviewed papers about the impact and the outcomes of FADs into other countries, I see the only thing that goes up is the suicide rate. So that's scary when the only metric that goes up is the number of people that take their lives because of the depression of these diseases. That's a very scary fact. Now, African swine fever virus, the topic for the day. In the words of Dr. Spronk, it's the world's worst pig virus. This is the worst virus a pig could get. You can see by the photographs there from around the world, this virus will kill basically every pig it infects. Easily over 90% of the animals will die from this virus. And it is a monster of a virus. I've never seen anything like it when you think about the virus itself. Now, a couple of things to remember. The ASF virus does not affect people. It only affects pigs. So pigs are the only species that can get ASF. And pork is safe to eat, even from an ASF positive pig. There's no danger about contracting African swine fever virus from eating pork. It can't affect or infect people. Right now, it's not in North America, and there is no effective vaccine, although there is quite a bit of work being done on that out at Plum Island off the coast of New York. There's the virus. Let's take a minute and talk about this virus. For those of you who are familiar with virology of this crazy virus, my goodness, it's what, 200 nanometers? So PRRS virus is about 40 nanometers in diameter. Some of the coronaviruses are 80 to 100 nanometers in diameter. This thing's 200 nanometers in diameter, so it's very large. It's got 160 open reading frames. PRRS has 7, basically. This has 160. So it's a very complicated virus. It's what we call icosahedral morphology. So you kind of look at that hexagonal shape. When you dig down and look at the EM here, you see a lot of protein. You see in the center, the nucleoid, the brain of the virus in the core. The brain, the nucleoid surrounded by the protein core, surrounded by the protein core around it. And then you see a little bit of lipid envelope. And then you see the capsid, the outer layer there, that's comprised of 2,000 capsomeres. So it's an incredible virus. It's like a big tank. Think of it as a big army tank, very bulletproof. So what's happening globally? I keep track of this every day as we get reports. This is now a disease of 3 continents. Many of you online today know more about this than I do, but I'm paying attention and I'm feeling bad for many of you because it sounds like there's a lot of outbreaks still happening in Eastern Europe. Many countries are infected. Gosh, now it looks like it's made its way into Germany from Poland. 65 cases in wild boar was what I read this morning. Hasn't got into the domestic pigs yet, which is fortunate, but it's in the wild boar in Germany and moving. The wild boar is considered a primary risk factor for this virus to move from country to country, but I'm going to challenge maybe some of the European perspective today on transmission of this virus. I want you also to consider feed. I'm going to show you some evidence why, besides wild boar, which is clearly the primary risk factor, you need to consider the risk of feed. Now, things really changed when the virus got into China. You know, ASF had been smoldering in Africa, had been smoldering in Europe for many, many years. It's been around for a long, long time. But things changed when it got into China, which was in August 3rd of 2018. You see the first outbreak noted there in the Shenyang area. And notice how the virus outbreaks have spread across the country of China into other countries of Asia. It probably came from Russia through Mongolia is what people are thinking. People movement, pig movement. We see how the virus has spread to other countries, Laos, Vietnam, Indonesia, Philippines, East Timor, Vietnam. So it's really moved a lot in Asia. And this is scary to the United States because we import a lot of products from Asia, and we'll talk about that. So whenever I think of ASF, what's happened in the world, I always ask what's new in China. And we have Dr. Joseph Yaros and Dr. Gordon Spronk from our China team who spend a lot of time in China. Obviously, they haven't been there for a while with COVID-19, but we have business in China. We actually own production. We manage production in China. So I asked Joseph and Gordon for an update. What do they think's happening in China that's interesting? Well, they say there's a lot of expansion. And then the national herd took a real hit. Estimated maybe 50 million sows in China before ASF, down to 15 million. Now the Chinese herd is rapidly rebuilding. It's probably even higher than 30 million sows right now. It's big bucks in China, in the pig area, in the pig markets these days. Wean pigs, last time I checked, were going for $250 US with a $40 cost of production. That's probably gone up. Gilts, anything that will breed, will go for $600 to $800 with a very low cost of production. Now, there's not much elimination of ASF happening in China. They're working on controlling it, but means there's wild strains still circulating. There's some vaccines being manufactured, although I think there are some good efforts to make safe vaccines. I think there's a lot of, I'll just call it black market vaccinology going on, which could be risky because they're modified live viruses. And so you've got rapid expansion with naive animals, you've got wild strains still circulating, and you've got some wild virus, vaccine virus strains that are out there too. So there's a lot of virus activity in the country. Now, the Chinese are very focused on the risk of feed. They believe strongly in the risk of feed. They found the viral DNA of ASF in the commercial feed system. And right now, when I talk to my colleagues in China, it sounds like they're actually trying to cook the feed, you see, for 3 minutes to 85 degrees Celsius to try to kill the virus. And so it's pretty crazy over there. It's kind of what I call the wild, wild east. Yes, and so how would feed play a role in viral transport and transmission? You think about that. How could something move from one country to another or from a farm to a farm? And I started thinking, well, perhaps the Trojan horse, if you remember the story of the Trojan horse, where the Greeks and the Trojan army were fighting for 10 years. It was a standoff. The Greeks gave the Trojans the Trojan horse as a gift of surrender. The people of Troy started celebrating. They went to sleep. The 10 Greek soldiers from inside the horse came out, unlocked the gates, and then the Greeks charged the city and took it over in basically one evening. So I kind of always use that metaphor of the Trojan horse because this is how grain gets dried in Asia. It's a cultural fact. It's been going on for years. Basically, the grain are harvested from the fields and placed on the roads where there can be contact with people, with footwear, with vehicles, with animals, and then it's moved on to other countries. And so I saw this for the first time maybe 9-10 years ago. It's very different, and we have to realize that this is a potential place that viruses could potentially contaminate the feedstuff. And as I mentioned, the Chinese have done a nice job of surveying this material, and they have found evidence of ASF DNA in the feed on the ground. And at a low percentage, it's not a very high percentage of positive samples, but they can find it in many different types of grains on the ground. You see corn, soy, rice, wheat, DDGs. So the virus is moving about, especially in an epidemic setting. If you think of a naive country that gets infected with a new virus, you're going to have a lot of virus into the environment, excreted from animals, excreted from dead animals, moved around by fomites, because the Chinese have also shown that ASF DNA was present in the feed mill environment, feed trucks and trailers, complete feed in the bins, on people, and in the fresh market. So think of it like almost like an atomic bomb goes off when these new viruses come into these susceptible national herds, and all of a sudden there's extensive replication and shedding. This is the same thing that happened in the US when PED, porcine epidemic diarrhea virus, came to the US. And so the science behind the risk of feed. Let's go to that topic now. And it really all started with PED. So there it is. There's porcine epidemic diarrhea virus. It's a coronavirus, as we know, about 80 to 120 nanometers in size. Now, let me take you to January of 2014, the first week or so of January, where I first experienced the potential for PED virus to be moved in feed. And I want to show you 3 example farms: Farm A, Farm B, and Farm C. Now these farms, one was in Iowa, one was in Minnesota, and one was in South Dakota, so they were in different states of the United States. We managed those farms. We were the veterinarians for those farms. And one thing was, very early in January of 2014, they all became infected with PED. And when we went back and did some on-farm epidemiology, we realized that the only thing in common between these farms is they were all filtered. They had shower in, shower out. They had transport sanitation. They had supply decontamination. The only thing that was really connected the dots was they had a feed outage. There was a bin on the farm that ran out of feed. And you see where that bin was located in each of the 3 farms, the West Gestation, West Farrowing, and North Gestation. So feed came to the farm, it was delivered on those dates, and it was consumed January 6th, January 8th, January 9th. The sows were hungry. And then all of a sudden we started seeing the index cases on the farm, vomiting and diarrhea in the same location as the feed outage serviced. So again, West Gestation, West Farrowing, North Gestation. We diagnosed the disease on, you see the 9th, the 11th, and the 13th. And then wondering about the risk of feed, I actually climbed inside the bins that where the feed outage occurred, and would scrape the insides of the bins with a paint roller on a long pole. And I collected some of that feed material that had hung up on the walls of the bin, because I thought that might be a good way to sample a large tonnage, in contrast to just taking a grab sample of a pound or 2. To me, it was more representative of the tonnage if I could sample the interior walls of the bin. And I found very strong evidence of PEDV RNA. So that's cycle thresholds there, 20.25, 22.6, 19.5 CT. For example, a negative value would be 38 or 40. So these are very strong CT values showing that viral RNA is present, indicating PED virus was in the bin. So that little picture there you see is from one of these farms. The bin on the right would have been the bin with the feed outage, where the index cases were being serviced, where I climbed down into the bin and collected the samples we just discussed. And right next to it, that bin on the left would be feeding another group of clinically normal sows on the farm, and you'd find no evidence of virus RNA in that feed. So that was really interesting. You could have it. It was that focused. That's what gave us the insight that maybe feed was a potential vehicle for this virus. So the next thing we did was we asked, is it live virus or is it simply just RNA? Let's do an experiment. We took the feed material. You can see it there in the little plate. We got some negative pegs. We let them consume it. And within about 3 to 4 days, they were starting to show signs of vomiting, diarrhea. We found PED RNA in rectal swabs. We saw histologic lesions of villus atrophy in these little pigs. And so we actually provided proof of concept that feed could be a vehicle for moving this virus, which was a big step forward. Before I did this experiment, I actually went to PubMed, or the National Library of Medicine, and started looking at what other papers could I reference and learn from in regards to the risk of feed and PED, and basically 0 citations came up. I've never seen a PubMed search where it's come up with 0. So I'm going, oh boy, I'm on my own. And this is what we found, and we published that paper, as you see. We started asking questions then about ingredient survival. Complete feed is one thing, but it's made up of so many different ingredients. Are there differences in certain ingredients' abilities to protect virus or not? So we took ingredients, we put them in little containers, as you can see, and we spiked them with a standard amount of virus at Eric Nelson's lab in South Dakota State University. We put these ingredients outside in a Minnesota winter beginning in January. You see the big bins there. That's where the feed was sitting outside, actually outside of my house. And I would sample the ingredients every month and see if there was evidence of live virus. And this table gives you a quick little graph, gives you a summary. So y-axis is days post-inoculation. So this study ran for 200 days. On the x-axis, you see many different ingredients. You see soybean meal, complete feed, meat and bone meal, red blood cells, DDGs, choice white grease, various amino acids, vitamins, corn, various animal protein products, VTMs from sows, nursery grow finish, and soy oil, and then some ingredients that were treated with a mitigant called cell curve that we'll talk about. But you see, I saw 2 different things here. I saw a group of ingredients where I was able to recover a viable virus, out to certain points in time. That's the blue bars circled in green. Soybean meal, for example, and this will be a common theme of my talk today, PED virus was viable in soybean meal for out to 180 days. So from January all the way through May, I found live soybean meal, live virus in soybean meal, which was astounding to me. And then there's other ingredients there you can see where the virus was alive for shorter periods of time. In contrast, in the red circle, there was no live virus recovered from those ingredients even 1 day after inoculation. So there seemed to be a very like a bifurcation almost. Either the ingredients were really protective or they simply did not support virus at all. We then started asking the question, how in the world did this virus get into the United States? And this will roll into our African swine fever virus discussion in a minute. And we went back and started thinking a little bit about how grains are dried. So if we know the virus could be in the animal trucks or people's footwear, and it's contacting the grain on the ground, could the grain get contaminated and then get moved around to other countries, including the United States? So we started there, and we started looking into what we actually import from China. And so here's some data from 2013 up through 2018, just showing you basically every year when I started working on this project. So we're now in about 215, 216. We import about 2 million metric tons of agricultural products to the United States every year. And so how do we demonstrate the risk of Chinese imports? Let's make a model. Let's simulate under laboratory conditions how product would move from China to the United States. So I went to a website called crates.com. You see circle up there on the left. And I found out, well, if product's going to come from Beijing, it's going to go to the Shanghai terminal, the Anqin terminal. It's going to cross the Pacific. It's going to enter in San Francisco, and it's going to be transported to Des Moines, Iowa, basically through one of our interstates, number 80. And so this is my route. And the C-Rates program told me this is going to take about 37 days because you've got transport time, you've got quarantine time in customs and such when it enters the United States. So I plugged that all into a 37-day study. And I took ingredients, and I'll show you what I did, but I took 4 sets of ingredients. So in quadruplicate, batch 1, 2, 3, 4, I inoculated these ingredients with PED virus. I put them in an environmental chamber to simulate the shipping conditions across the ocean and across the land. And I tested them for live virus at Eric Nelson's lab with the help of Diego Dial and Eric at 4 different points. And so each batch got pulled out of the incubator at day 1 post-inoculation, which was to represent the Beijing time, at day 8 post-inoculation, which was the time it took to get to Anqin terminal and to become ready to disembark. And then batch 3 across the ocean enters San Francisco, goes into customs for a week. And then batch 4 into Des Moines after it's transported across the highway. Here are some of the ingredients we chose. We went to the US government harmonized tariff schedule, which is a public website that records all of the products that are imported into the United States. And I asked, well, what comes in to San Francisco? Because that was in our model, it's going to be our port of entry. And you can see the ingredients there that we bring in kilogram amounts year after year after year. And so we bring a lot of interesting things from China: soy products, DDGs, pet foods, pork sausage casings, and vitamins and amino acids. And so we were wanting to be representative. We selected these ingredients and put them into the laboratory. So there are the ingredients in little tubes up in the red caps there. We weighed out a standard amount of each ingredient. We transfer the ingredients to the middle picture, the orange cap tubes. They're vented caps, so the viruses and the feed can feel the effects of the environment, which I'll explain in a moment. So we're taking the feed, we're spiking it with a standard amount of PED, we're putting on these vented caps, then we're moving it into this incubator called an environmental chamber that you see there. This is like an incubator with a computer, and you can program the computer to change temperature and relative humidity over time. So I wanted to kind of simulate the environment that feed ingredients and viruses would experience when they're moving across the ocean. And I went and found information in regards to temperature and relative humidity in China over the Pacific Ocean and into the United States over the time of December 23rd, 2012 up to January 28th, 2013. So I'm simulating a period of shipment prior to PED arrival in the US. So PED was first discovered in the US about April of 2013. I'm kind of setting this up to say, well, what if the virus is heading our way? And I found data from Weather Underground in regards to the temperature every day of our 37-day experiment. You see there on the x-axis, and then relative humidity, same information. What was it like in that parameter on land and sea? Over sea, it was interesting. I didn't have real good access to data for what's happening over the ocean, but I did find a paper from the Xerox company where they actually put data loggers in their containers as they move their paper and their ink and their printers across the ocean. They were studying the same thing. So I was able to actually take specific data over the ocean, which was really cool because that was very hard to find, and plug it into the environmental chamber. And so these are the means, as you see here. At each day of the 37 days, these two parameters are cycling 4 times a day, based on actual temperature and relative humidity points that came from this information. So I'm trying to, again, make it almost like a crime scene investigation where we're going to see if we can reproduce the crime, reproduce the movement of the virus. Now, ASF, this is probably 2017 now. ASF hadn't been announced in China yet. It hadn't been discovered that it was in China, but it was in Eastern Europe. And so I set the same approach up to simulate the movement of ingredients from Eastern Europe to the United States. And I went again I followed the whole procedure as I just described. We're going to start in Warsaw, Poland. We're going to go to Le Havre Terminal in France. We're going to cross the Atlantic and enter New York City. Then we're going to transport over to Des Moines. I'm going to set the same thing up. So quadruplicate batches of ingredients spiked with ASF virus put through the environmental chamber. Now, as you all know, there's no surrogate virus for ASF, and I only have BSL-2 capabilities. But I was very fortunate to work with Dr. Megan Niederwerder, a close colleague of mine, I think one of the best virologists we have in the United States, a real driver in this feed risk. And so Megan and I worked together, and she had the ability in the BSL-3 facility at Kansas State University to work with the actual ASF virus. So we put the real virus under very safe laboratory conditions into our ingredient model and simulated its movement from Eastern Europe to the United States. We did the same thing with temperature and relative humidity. Megan got an environmental chamber, and it would cycle every day 4 times, again, changing the temperature and relative humidity 4 times a day. Very cool story here about the oceanic data, very difficult to find. I searched and searched, and I finally found a PhD thesis from a student at the University of Reykjavik in Iceland, who was studying temperature and relative humidity in containers shipping codfish in the North Atlantic. So here I had a beautiful data set of containers moving across the Atlantic, in the North Atlantic, where I could take those informations from that thesis and probe them into the environmental chamber. So it really helped make the curve representative, so the environmental curve. And we're going to use this environmental curve many times as we work with ASF. So what did we learn from all of this? We did this with many viruses. This has all been published. This is a summary from some of the papers I've written, as well as from Anna Stoyan, who is Megan's graduate student. This has all been published. This is the batch 4 sample from the Trans-Pacific, the day 37 post-inoculation, or the Transatlantic, which was a 30-day journey, a little shorter than the Pacific journey. So this is the batch 4 you saw from the maps. This is a question. This is the virus still alive in regards to at the end of the journey? So if we take that 4th batch of samples, we test it for viable virus, can we detect it either by virus isolation or swine bioassay? So here you see on the left the ingredients that we've been using in all of these studies, the soy products, 3 different soy products. Conventional soy, that is the high protein, low fat version. Organic soy is low protein, high fat. Soy oil cake is a remnant from the soy oil processing that comes over for use in feed. DDGs, lysine, choline, vitamin D, 3 different types of pet foods, moist cat, moist dog, dry dog, the pork sausage casings again, complete feed as a positive control, spiked with virus, complete feed as a negative control, so spiked with saline. Then a stock virus control is simply the virus by itself in the tube without a feed matrix, trying to see whether the virus can survive on its own or is the feed matrix important for survival. So on the top of this, moving from left to right, you see the viruses we tested. SVA, that's Seneca virus A, that's a surrogate virus for FMD. They're picoRNA viruses. They're very similar in size and shape. There's ASF from Megan's lab. Pseudorabies, again from Megan's lab. There's the original PED work we did. Note we had a little bit different ingredients for that first experiment. Porcine sapellovirus, that's to surrogate for swine vesicular disease virus. Classical swine fever virus, that is again from Megan's lab. PCV2, PRRS virus 174, vesicular stomatitis virus, and then influenza virus of swine. Now look at this chart. Everywhere you see a red box, that's where we detected live virus, either by virus isolation or by bioassay. So if you just look at ASF and go down the column, we found live ASF and all those ingredients, all 3 soy ingredients. Where there's green, then it was negative on VI, negative on bioassay. So no recovery from DDGs, no recovery from lysine, recovery from choline in a viable form, not in vitamin D. You see all the pet foods and casings were positive. The complete feed positive control was positive, and even the stock virus control was positive as well. So this virus is so stable, it actually lived in the test tube in the absence of the feed matrix. So fascinating. You can kind of get a feel here. Some of these viruses live very well in feed. Seneca, the FMD surrogate, pseudorabies virus, PED virus. Some of these viruses live very well in feed while others don't. CSF virus, for example, is only detected in 2 products. PCV2 only in 4 products, and then PRRS in 2. And then in VSF, vesicular stomatitis virus and influenza, there was no survival in our journey. So look down the column, now look across the row. Look at soybean meal, look at all the red. Look at all the red in the soy products. That's again the theme, the repeating theme here, that some of these ingredients are very protective for viruses. Why, I don't know. But see that here. Some of these ingredients, such as soy, are very, very concerning to me because viruses seem to enjoy spending time in soy products. So this was kind of the first step to kind of see, well, could the virus live over the ocean in a controlled laboratory setting? And we published that, as I mentioned, in the +1 journal, and it's available open access for you if you want to take a look. Now, Megan followed that up with some great work looking at ASFV transmission through feed and water. She actually took varying doses of ASF, allowed pigs to either drink contaminated water or complete feed naturally. So this wasn't a bioassay where she force fed. They actually went up to the feeder multiple times a day and consumed. What she learned was transmission of ASF virus was very easy to do through water, a little harder to do through feed based on the oral infectious dose. And the probability of infection was really driven by frequency of exposure, not dose. So the more often the pigs went up to the feeder and ate feed during the day, the higher the frequency of infection, which makes perfect sense. So the more often a pig consumes contaminated feed or water, the lower the dose of virus necessary to infect. So this was a seminal paper that Dr. Niederwerder and her team published. They also did a great study looking at the half-life of ASF virus in feed. This is Anna Stoyan again. This is Megan's student. She's published this in Emerging Infectious Diseases. They took our transatlantic model that they had set up in their lab. They used the ASF Georgia strain, and they tested viral survival and calculated half-life throughout the 30-day journey. So they replicated the survival study. They showed, as we just kind of demonstrated in our red and green chart, that there was viable virus in 9 of 14 ingredients over that 30-day model. And titers decayed originally from the initial spike of 5 logs TCID50 to 3 logs over this 30-day period of time. So there was some viral decay, but there was still 1 × 10⁻³ TCID50 in these feed samples after this 30-day period of time. And from that, they went on with the help of Jeff Zimmerman from Iowa State University, and they calculated the half-life. And they found that the mean half-life in all 9 ingredients was approximately 12 days, with a range of 9.6 to 14.2 days. And you can see the paper, and you can look at each of the ingredients that demonstrated a half-life. So the bottom line here was ASF survives much longer than the 30-day study period. Great work. So now we've got ASF in raw materials. We've shown you Chinese data. We've got ASFV survival in transport. I showed you the red-green chart. You saw how well this virus lived in a simulated transport over the sea. And then Megan has shown you, as we just reviewed, the transmission is possible through feed. So we're starting to connect the dots here. Now, the next question was, where does it enter? Where do soy-based products, because we're concerned about that from the protective nature of soy, where do they enter the U.S.? Are there certain ports where we're going to have a higher risk of from an ASF positive country to where soy imports would be coming? And so here we go to the tariff schedule again. We ask some questions. How much soy-based product did the U.S. import from ASFV positive countries 2018, 2019? What are the primary ports of entry, and are there trends over time in ports of entry? Gil Patterson, my friend from Veterinary, who's been an important part of all this work, he's got a really nice program where he'll take information from the tariff schedule and put it into pivot tables, and he'll be able to answer these questions. And this paper just got accepted yesterday, Transboundary Emerging Diseases. So just a couple of tables from the paper just to show you what we learned. So country of origin is in 2018, 2019, here are the countries that we imported soy-based products from into the United States. There's in metric tons the amount in 2018, and then 2019, if you go over a few more columns. And what you see is we bring in the majority of our soy-based imports in those 2 years came from 3 ASF positive countries: Ukraine, Russia, and China. And down at the bottom, you see the grand total of the metric tons, about 104,000 metric tons in 2018 and 73,000 metric tons in 2019. Now, so we know kind of where the bullets are coming from, where the guns are that's shooting the bullets at us, right? We know that there are soy-based imports coming from these ASF positive countries. Now, to put it in perspective, the 104,000 metric tons that we imported in 2018 is that little sliver of red as it compares to the whole pie of exports from the United States. So this is a teeny little slice. It's almost ridiculous that we're dealing with this small slice of pie compared to what we export. Now, what about the ports of entry? Here's a couple of charts. We're going to look at China first and then Ukraine. So here's metric tons on the y-axis. You've got time on the x-axis, different years, 2015 through 2019. And there you see from the work Gil Patterson did, where are the primary ports of entry from China? And as you'd expect, a lot's coming in to San Francisco, and you see that blue line at the top. Now, the good news is, if you go to that red arrow, in 2018, when the announcement from China occurred that they were ASF positive, look at the trend line now, down to 2019. So there's been a big drop. I think it's 55,000 some metric tons down to maybe 6,000 metric tons over that couple year period of time. That's good. And you ask the U.S. Soy Board why, and they say basically it's because of the research that we've just reviewed, all the work we've talked about, and then the press, the industry, the swine industry, putting that information out into the press and raising awareness and putting everyone on high alert that, you know, there's a risk here. Look at the nice impact that's had on reducing imports from China. And we'll see what happens in further years, but that's a nice change. Ukraine's very different. Ukraine's kind of scary to me because material comes in, soy products come in from the Ukraine all over the place. And you can see it changes from year to year. It might come in from San Francisco. It might come in via New Orleans. It might come in via Charlotte. And so It's not nearly as stable of a import pattern as we saw in China. So China gets a lot of bad rap, but I think we have to also pay attention to the Eastern European countries that we're importing from too, that are ASF positive. And Ukraine, as you saw from the table, along with Russia, are two of those. So what are we going to do about this? You know, this was a whole new room we entered. The fact that feed was even considered a vehicle for virus movement before PED, no one ever thought about that. This has changed everything as far as how the United States handles its feed importation. And this has really been industry driven. I have to give credit to the swine industry. And one of the things that we put forth in 2018 from our group in Pipestone was this concept of responsible imports. We know that there are some ingredients we have to bring in from other countries because they're not made in the US. We know that the cost savings are so significant to our producers. Can we safely bring them in, say B vitamins, certain trace minerals, amino acids? Can we bring them in safely using science? And so that's the objective of responsible imports. And you look at the questions. These are the questions now we ask of the country of origin in regards to what's the ingredient, where is it coming from, is it ASF positive country, are there alternative ingredients that we can use, are there alternative sources, what's the virus we're worried about? Well, today it's ASF. Do we know its half-life? Yes, we do. What's the transport time it takes from source to the mill? That's never been asked before. Has any mitigation been applied? And can we then store the material for a period of time under a standard temperature and allow time to decay viral load? It's almost like you put it in quarantine. This is basically very similar to how we handle the entry of breeding stock from other countries. It's almost like a health paper that the feed has to have now. So let me show you how we do it in Pipestone. I'm going to talk about our responsible imports plan beginning in China and then into the United States. And so we are bringing amino acids and VTMs in from China for our producer customers. It's under the leadership at the China side of Dr. Arkan Wu, who's one of our PhD nutritionists. He's from China, so he knows the language. He goes to China. He oversees manufacturing plants and port warehouses. He'll audit those facilities a minimum of twice a year. He'll put in basic standard biosecurity protocols that we use on pig farms. Lines of separation, clean, dirty, use of PPE, going to one-time use totes, and then using containers that are sealed at the plant and not open until it reaches the final US destination. So here are some photos from I think it's a vitamin manufacturing plant after Arkan's visit. Upper left-hand corner shows you a bench where before you can enter the facility, you have to sit on that bench, take off your shoes, spin your feet around, and move forward on stocking foot, put on PPE in the cabinet there on the right, and then through the door you go into the facility. Now look how nice and clean these facilities are. These are really high-class facilities. And there you see the warehouse in the upper right-hand corner, covered with plastic over all of the bags. And I think the biggest thing Arkan did was down in the bottom left. The bags used to get transported from the plant to the port on a flatbed, open to the air, open to environmental contamination. That got changed. Now it's being done this way. You see bottom right-hand corner, one-time use totes at the manufacturing plant, put in a sealed container that's not opened until it enters the United States. So a much tighter biosecurity in regards to movement from plant to port and during shipment. Now, once it comes to the United States, it goes to a specific warehouse organized by a group called SAM Nutrition out of Minnesota. Under the leadership of Roger Cochran, our feed mill manager, SAM Nutrition and Roger have put in kind of the same approaches. Separate entry and exit points for people and products, a sign-in book. I'll show you some pictures, as well as mechanical biosecurity protocols throughout the facility. They've even set up a quarantine room where the products come off the container, they enter this quarantine room. I'll show you a photograph. It's got its own entry, it's got its own forklift. It stays in that quarantine room for a minimum of 30 days and 20 degrees Celsius. It's a true all-in, all-out space. And then in the storage area, products are nicely labeled and kept clean. It's heated year-round, and the facility is audited twice a year. So a lot of credit to Roger, but also to SAM Nutrition for going above and beyond. Here's what it looks like. Here's the warehouse. The red arrow is where the containers are unloaded, so a specific door. The yellow arrow is where the personnel and drivers enter, so the 2 separate staircases and 2 separate doors. And the green arrow shows you where the products leave. Okay, so separate entry, separate exit. Below that picture, you see a footpath. When the driver walks in through that door into the office, he or she has to step into this footpath. Below that's the sign-in book where the driver signs his name, what date is, where he's been. The middle top picture you see is what he sees or what she sees when he comes in. That's as far as they go into the warehouse. They're not allowed any farther than that desk where the sign-in book is located. Below that, you see the warehouse. Very, very nice control. All bags covered in plastic, all labeled by product. And down at the end of the hallway there, you see an opening. And that's that picture in the upper right-hand corner. That's the entry to the quarantine room. There you see the quarantine room. And to get into the quarantine room from the warehouse or vice versa, you have to step in a footbath as you see. You have to put on PPE. And then the quarantine room is closed with that door, the final picture for the 30-day period of time. So it's a true all-in, all-out quarantine. It's a beautiful piece of work, and it gives us confidence that we can bring in these products from ASF-positive countries, save our clients a ton of money, and do this for about 1.5 cents a pound. That's what that's roughly costing us now to do all of this work. It's great to have partners like Sam Nutrition who are so dedicated to biosecurity. They want to go above and beyond. The other thing we're doing is looking at feed additives as mitigants. We just published a paper in Transbounding Emerging Diseases looking at if there were certain additives we could put in the feed to reduce virus survival. And I set up a new model basically in our BSL2. You see that there. This has got 6 independent rooms with air filtered in and air filtered out. So you can have treatments and controls side by side. We're gonna have 100 pigs in a room in this experiment. Each room has a designated feed bin, so we can have treated feed, mitigated feed, or we could have non-mitigated control feed. So we're trying to ramp this up. We're gonna use tons of feed, hundreds of pigs, and see if any of these mitigants actually work. Here is a list of companies that were involved in this study. I wanna recognize all the companies and the products they brought. They brought funding, they brought products. You can see the list of products and the list of companies that were involved. So you go down that list, you see organic acids, you see formaldehyde products, you see medium chain fatty acids, you see essential oils, you see prebiotic fibers, and various combinations. And so all those companies played a major role. Now, you see I've highlighted 2 companies with red asterisks, Alltech and Guardian. That's I developed that product in Pipestone, so I have a conflict of interest to share with you. And then Cargill, Vigilex. Vigilex, we wanted to test Vigilex because it was very popular, but the Provimi group from Cargill didn't want to do it, so they kind of pulled out. But some of the producers that we do research with wanted it in there, so they paid the money to get it tested. So that's kind of the asterisk, double asterisk there is that group did not provide funds while everybody else did. We challenged with an ice block model. So we took PRRS virus 174, PED, and Seneca virus. Remember, Seneca is the surrogate for foot and mouth disease virus. PED, of course, you know. And PRRS virus 174 is a very representative, highly virulent strain of PRRS right now in North America. We froze those viruses all together in an ice block in Eric Nelson's laboratory, each at a log of 10 to the 5 TC8050. So this is going to be our challenge. We're going to take that block of ice, we're going to climb up the ladder of the bin and drop that block of ice in the feed and let Mother Nature take over and auger in the block as it melts or as it chips and contaminates the feed, kind of a hotspot point of contamination. We ran 5 experiments. I'll show you just one. For example, I just pulled one randomly out of the study. So this is experiment 5. You see in this case, we were testing 5 different products. They're listed there at the inclusion rates in parentheses. And we always have a positive control, which is a room of 100 pigs, each eating, non-mitigated feed. So we've got treatments, 5 treatments noted here: PH Horse, Dofit Plus, Dual Defender, First Protect, and Vigilex at their inclusion rates. And then you see just some of the performance differences we saw during the study. And you could read the whole paper and get all the information. But notice that the first 4 mitigants had a very positive effect in mitigating those 3 viruses. We had very good average daily gains. We did not see that with the Vigilex product. There was no difference statistically than the positive control. We recovered all 3 viruses from the Vigilex pigs and the positive control pigs, and saw illness of all 3 diseases in those 2 rooms. Not the case in the mitigated rooms, and you see the numerical differences in mortality. And if we do a meta-analysis across all 5 experiments and just look at average daily gain, and you look at the forest plot there on the right, you see that in all 5 experiments across all those 15 products, it favored the use of a mitigant. You see there on the 0 line, everything is shaded to the right, favoring the use of a mitigant. And what we learned kind of concluding that study was we saw improved health and performance observed in mitigated pigs on mitigated diet versus non-mitigated diet, even in the face of infection. We could still find viral RNA in our treatment rooms, in our treatment pigs, but we didn't see disease. We saw great performance and very low mortality. It's almost like the mitigant had an ameliorative effect and reduced the effect of the virus. So 14 out of the 15 products we tested performed similarly. As I mentioned, 1 product did not work very well. I just showed you that slide. And we were happy with this because we were able to test many different chemistries, many different types of products. We looked at different inclusion rates and costs, providing options for producers. So take a look at that paper. I don't have enough time today to get into it all. So closing here, we're going to kind of see what impact we've had so far. At the governance level, the Canadian Food Inspection Agency has taken all the work we've talked about and put a plan in place. So come March of 2019, began in 2019 and is carrying on yet today. As products come in from high-risk countries with ASF, they go into a secondary control zone and are stored for a period of time, just like we talked about. At the national level, great work by the Canadians. Our responsible imports idea, actually we wrote a policy which was approved at National Pork Forum in 2020 for use in the United States. And then in 2020, an NPPC wrote a letter to our Secretary of Agriculture, Dr. Sonny Perdue, and stating the need to work with these high-risk products coming from high-risk countries. So soy-based products, for example, coming from ASF-positive countries, signed off by all 31 state and national organizations for pig production, requesting that Secretary Perdue step in and we develop a plan to control these imports, not necessarily ban them, because that's difficult with trade, but to control them, perhaps restrict direct importation to the United States. So it's interesting times as we get ready to close. I've even worked with the FBI, Weapons of Mass Destruction Division. They've been interested in the risk of feedstuffs as vehicles for foreign animal disease entry to the United States. So I worked with that group. They're fantastic. They gave me what's called a warrior chip, which is this nice little chip here, the front and the back. So that's a little token of their appreciation I carry with me. So you never know when you're a young boy growing up wanting to be a vet, what you might see, what you might do in your career. Last slide before the questions. I think I've tried to show you that there is a growing body of scientific evidence that certain feed ingredients can support the transport and transmission of ASF virus and other foreign animal disease agents. There's a lot of science now that shows that this could happen. We've got options to mitigate this risk, be it holding time, be it additives. And this information has brought a positive change in human behavior at the level of veterinary profession and the swine industry, how we're managing imports, almost quarantining the feed. That's changing human behavior. However, we have not made progress yet at the federal level. And I'm hoping that we can work with USDA and FDA to try to develop more of a national program like the Canadians have done. And with our high-risk port understanding, we can focus resources at these ports. So we still need some more collaboration across the industry. And with that, I think I'm near the end of my slide deck. I think I will close. I will thank Balchem Animal Health and Nutrition for inviting me. We went fast, and so you might have a lot of questions, but you can see the story of my life in the last 6 years. It's been crazy. So I do appreciate the time, and I'm open for questions, and I'll turn it back to Mr. Sorrell.
Thank you, Scott. Before we get started answering questions, we'd like to share a brief video, and then we'll be right back to answer the questions submitted during today's presentation.
As the global leader in choline, Balchem has spent more than 50 years perfecting the art and science of choline chloride production. The new Puricol line delivers the highest standards of quality, produced in state-of-the-art manufacturing facilities, and backed by the strictest process controls for a level of purity, safety, and consistency you can't find anywhere else. Turn to Puricol choline chloride from Balchem for an unmatched level of quality you can trust. Visit balchemanh.com to learn more.
All right. We've had several origin-related questions, and I'll start there. Seems like a nice place to start. What do we know about the origins of African swine fever? We know or believe that the coronavirus came from bats. Where do we think ASF came from? Did it originate in wild pigs, or do we believe it jumped from another species?
That's a good question. It's probably a little beyond my understanding of the virus. I would speculate that this is a pig virus, and it's always been a pig virus. It's so stable, and it's a double-stranded DNA virus, and it really only infects one species that we've ever been able to demonstrate, and other species have been attempted under experimental conditions to see if they could become infected. But I don't think they've ever successfully infected another species. I think there's some data that shows it might be living, of course, in ticks. We know that. That's how the ticks move it around in certain climates. I think other insects like mosquitoes might be able to move it around. But as far as its origin, I think it's strictly a pig virus, but I could be wrong.
Now, you said it's transmitted by humans, mostly fomite oriented. Do you know if it can survive in humans?
It cannot. It cannot survive in humans. It cannot infect a human. Of course, it could be on your shoes if you've got contaminated footwear. And this was blood, for example. It lives in blood high quantities for a very long period of time, especially in their cold weather. So you can mechanically move this thing around on your hands, on your feet, but you cannot become infected and become a human carrier that could transmit the virus from a human to a pig. So I'm quite confident about that.
Okay, kind of keeping with that same line of thinking, has the wild boar population developed any level of herd immunity, right? We've heard a lot about herd immunity. And if so, to what degree and what implications might that have for developing a viable vaccine?
I believe if the pigs survive, there's good protection to that, homologous protection to that strain. I think the challenge with ASF is one virus does not protect against all other viruses. I think that's one of the challenges with making a vaccine. You have to find that commonality across all these viruses and try to make a vaccine that directs immunity towards that epitope, for example. But I think homologous protection is quite good, but heterologous protection is limited.
All right, thank you. The next question is related to the ability for the virus to survive on feed ingredients. And specifically, we saw that the soybean meal is able to survive for 180 days, but 0 on corn. How do you explain the dynamics behind that?
Yeah, great question. I've asked that a lot to my nutrition colleagues, and really nobody knows. But I think the best hypothesis is the potential for high protein plant products to serve as in a protective way. You look at corn, it's a lot of carbohydrate. Soy's got a lot of protein. Even the organic soy we studied, that's more of an expelled, extruded variety. So the fat level is higher and the protein level is lower than the conventional. But I think that's if you ask 10 nutritionists, you might get that answer on a regular basis. But I don't think anybody really knows.
All right, and then the study has showed that was oriented toward soybean meal products coming in from Europe. But we know that China is a hotspot for African swine fever. And so what kind of products are coming in from China, and what kind of risks, what's your thoughts related to that?
Well, we do soy products is my biggest concern. Bulk ingredients, bulk feed ingredients are tough to manage. You know, their volume is so large. It's hard to quarantine or hard to hold bulk products for a period of time. It's actually quite easy to work with vitamins, trace minerals. And I believe just from our experiences with the high quality of production of those products in China, the risk is very, very low on those fine ingredients. To me, the big elephant in the room are the soy bulk, the big bulk products like soy that come in. Because you've seen from the red-green table and all the work that Megan's done too, for some reason, ASF lives very well in soy. So that's my biggest concern. I wish we could control that better. I wish we could restrict entry some way and mitigate prior to putting that material into the domestic feed supply.
All right, and I'm mindful of our time here. We're a little bit past the hour. So we'll have this last question from Rob. In the BCL2 study, what is the MOA, mode of action, for the different mitigants and their ability to reduce viral infection and mortality? Is the effect on the virus or on the host?
That's a brilliant question that I don't know the answer to. It could be both. I bet some of these products have immune enhancing potential. That's been shown in some of the products that we've worked with, some of the essential oils, for example. I think the acids and the aldehydes have a deleterious effect on the virus. And so there could be a killing effect. There could be a viral load reduction effect. We saw that with our measurements when we sampled in that experiment. I didn't talk about it for time, but we took samples of the feeders to see if the viruses were present. We took samples of the oral cavities of the pigs to see if they contacted the viruses. And we also showed evidence of, and we also sampled pigs that were clinically ill or clinically normal to see if we could find the viruses in the animals. We did in almost all cases, especially the non-mitigated pigs. The viral loads are extremely high, meaning a lot of replication. In the pigs in the treatment groups, other than the one, very healthy, great performance. We could still find RNA, but the values, the quantitative values, were very, very weak. And so there seemed to be some effect on viral load as well. So I don't know the exact answer, but those would be a couple of hypotheses I'd formulate. Good question.
Well, that's going to do it for us today, folks. I want to thank Dr. D and thank you, everyone, for attending today's webinar. If you have additional questions, please submit them to anh.marketing@balchem.com, and we'll forward them along with the unanswered questions from today's session. This month, Balchem is launching an extension of the Real Science Lecture Series in podcast form called the Real Science Exchange. But this won't be just any boring podcast. You'll get to know top researchers like you've never known them before. Go behind the scenes and hear the conversations that take place over a few drinks with a few friends. Join us as we discuss the hot topics in animal science and share a range of new ideas. Search for Real Science Exchange on your favorite podcast platform, Apple, Google, Spotify, etc. And if you're so inclined, a 5-star rating is always appreciated. Dr. D will be joining us on a future episode, so be sure to subscribe to catch that. The next Real Science Lecture Series webinar will be on November 10th instead of our regular first Tuesday of the month due to the elections in the United States. Dr. Marina von Kaiserlink from the University of British Columbia will continue our discussion on social responsibility with a presentation titled Animal Agriculture, Renewing Our Social License. Visit balchemanh.com/realscience for more details and to register. On behalf of Balchem and Dr. D, thank you for joining us today.